Swayam Prabha. Digital India. Educated India.
Welcome back to this lecture series on foundations of cyber physical systems. So, I believe in the last lecture we were talking about the standard responses for second order systems. So, just starting from that point. So, what we talked about was that, well, a typical second order systems transfer function will be like this, right? I mean, this is the closed loop transfer function, and when you look at the poles of this system, I mean, for the underdamped case, you would have a set of complex conjugate poles, right? And for the different cases where the poles will be located otherwise and what will be the different step responses, we have already discussed. And so, in general, if we just take the responses together and plot in a common plot here like this, so typically this is how it will be looking like. So, what we want is that, well, if you are going to implement a system, it should respond fast, right? So, typically we will consider this underdamped case. This undamped case is not very useful because, well, it's an oscillatory output here. So, in general, for the underdamped case, if we take the poles, and of course for underdamped we will have this zeta value taken in a way like it's between 0 and 1, so that you have this complex conjugate poles here, so that the imaginary values, imaginary parts magnitudes are same but with opposite signs, as you can see, and the real part is negative here. So, if we just try to correlate like this, here you have these two pole positions, right, with the real part like this minus zeta omega n and the imaginary part given by these values. Okay. And of course, if you just write this equivalent part of omega n times square root of 1 minus zeta n square, if you just write it as omega d, so that would give you the natural frequency of the oscillations. So, there are two parts here. You have this real part which is having this damping ratio here, and you also have this imaginary part. So, as we know that the imaginary part is going to be indicating the oscillations, right, because the oscillation frequency will be governed by the imaginary part, and the real part will be taking care of the real part is having a negative damping value. So, that is taking care of the fact that, well, you have an exponential decay on this curve. So, in effect what you have is a sinusoidal oscillation, right, which is generated by this imaginary part, and if you look at the real part, like we have been saying, that it is primarily dictating the amount of damping, and you can actually see that if you connect these crest positions of this each of these maximas here, if you connect them, you get something like an exponential decay curve, and the rate of decay is kind of governed by this damping value. So, if you just like we talked about the response, the step response of a first order systems, if you just look at the response for the second order system, you can similarly create some specifications like what is the maximum overshoot. Let's say you are targeting this reference 1, okay, and so with respect to 1, the amount of overshoot you have here at the maximum point, so that's the maximum overshoot. Let Tp be the value denoting the time when this maximum overshoot occurs, right, and the rise time is when you are crossing over here the 1 value, okay, and then let's say you have a settling time criteria which says that, well, after points, by the time when this curve will settle down near 2% or 5% of the target value. So, different places you will have different settling time criteria, and accordingly you can have this TS design. And also this time by which you are climbing up to this 50% of that target reference, that is like your delay time. So, you have delay time, rise time, the peak time, the maximum overshoot that occurs at the peak time, and the settling time specifications. and it can be easily derived that well for all this. You can actually link up those values with the zeta and omega n's. Okay. So just to summarize, the delay time is the time required for the response to reach half of the final value the very first time. So as you can see, it is this much time, the delay here. Then you have the rise time, which is the time inside which the value will go from the 10% to 90% of its final value for the overdamped system. And since we are considering underdamped systems here, it is the time by which you are going from 0 to the 100%, that is the reference value, which wherever we are crossing the reference line up to that much, that is the rise time here. So by 100% we mean the final value exactly. And for peak time, it is the time when you get the first peak of the overshoot, and it can be shown for this curve that this occurs exactly at some peak time whose value is related to omega n and zeta by this equation. And based on what is your settling time criteria, whether it's a 2% settling time, whether you want it to reach and stay, you want the response to reach and stay within 2% of the final steady state value, or the 5% of the final steady state value, you can actually calculate that corresponding time. And if it is 2%, then it is 4 by zeta omega n. If it is 5%, it is 3 by zeta omega n. And similarly, you can also calculate the maximum overshoot, which is the maximum peak value of the response. The amount by which you cross over from the unit value, which is the target reference here. Now, if this final reference is going to, if the final steady state value, which was unity in this case, but in another case if it is differing from unity, then it is generally the maximum percentage overshoot. I mean, if it is unity, then you don't have anything here in the denominator, but otherwise you can just calculate using this formula, that what is the maximum percentage overshoot. Now, let us say you have this curve here, okay, of the oscillations, and you are trying to understand that, well, based on the position of the poles, how does the nature of this curve change? So suppose you have the real part which is negative, that to be constant, and your poles are located at these positions 1, or these positions 2, or these positions 3. That means the value of the imaginary part, let's say it is increasing. So if that increases, it would simply mean, if you look at the corresponding curves here, you are getting the responses with higher amount of oscillatory behavior. So that means you have you are having more amount of frequent oscillations in the response. But since the real part is same, that means the damping envelope, that is exactly same for all these curves. Now let's consider the other thing. Let's say the imaginary part remains same, but let's say the poles are increasing with respect to the with respect to the real negative real part. You are going more towards the negative axis. So with 1, you have these situations marked here with x, and this is the corresponding curve here, right? And if you look at the other position, x, for that you have this corresponding curve here. Now observe one thing, that what we expect, that the imaginary parts are same, that would really mean that the frequencies remain same. That actually is the case, but you understand that if the real part becomes more negative, you are essentially increasing the damping. So here if you see with green, you are going to get a response which is much more damped, and that's what is happening, right? The green one damps faster, the oscillations are damping faster, although the oscillations are having the same frequency. And consider this thing, that let's say you are moving along the diagonal. That means well, you are changing both of these values together, right? The real part and imaginary part both are increasing proportionately, right? So in that case your poles are migrating like this. So in this case what you expect is, well, the damping should increase and the oscillations should also increase, right. So, if you see here, this was the behavior for 1 with a bit more of damping and a bit more of oscillation, you have this, and with an even more bit of damping and even more bit of oscillation, you have this, right. So, both the damping and the oscillation is increasing, as you can see. It is going down faster, but also the fluctuations are increasing. The amount of fluctuations is increasing. But in all these cases, what is happening is the overshoot remains same, because if you try to think that why that should be the case, just look at the overshoot condition. So, it's like a ratio here, right. So, that will be one reason for that. So, the next thing we will like to talk about here is we understand that how first order and second order systems behave, and one good reason why we were talking about first order and second order transfer functions suddenly is that it is quite common in case of dynamical systems that a system may have complex behavior, but you will like to approximate that behavior around that operating point to generate a set of second order or let's say a first order approximation of the system. Now, in case you are doing that and you want to analyze interesting properties of the system, this can be one way to go about it. You can check its behavior in terms of stability, whether the response is oscillating or the response is not oscillating, whether the response is as you want it to be. You can look at those things and decide whether you are happy with the system or you want to modify the system in that sense. Now, we saw one thing here, which is like there are certain aspects of the system. For example, specifically if you consider these situations, let's say this situation. So, if you have don't know damping here, you have an oscillatory behavior, right. Or let's say it's zeta greater than 1, it's over damped, there is no oscillation because there is no imaginary component, but it is slow to respond, right. So, the point we are trying to make is from these different possible curves of output that we can see, we have an idea that well, systems can have oscillatory response, system can have a nice damped response like this, but none of these are like mathematical techniques which tell us that well, if I am given the state space model of the system or if I am given a transfer function model of the system, how do I really analyze whether that system is stable or not. So, before getting into this part, if you remember, let us go back once. So, this was our idea of the state space model, and then we said that well, what are the advantages of state space model. Just recapitulating a bit, you can model MIMO systems, you can create time invariant system models, you can model in general linear systems, you can also have time varying system models using this concept of ABCD matrices to represent the system where A and B can be a function of time, or A and B ABCD all of them can be constants. So, this is quite a nice and powerful model of representation, a model of system modeling and method of system modeling. And then we have by now also talked about the transfer function representation, which gives us a Laplace domain representation for LTI systems. And we have seen that well, how these different kind of under certain restrictions like being first order or second order, what are the expected response curves that we can get for such systems using standard test signals like the unit step or the impulse response, etc. Now, from this we have been saying that we understand that based on the pole positions of the system, we can see that well, what can be the responses, whether there will be oscillations, whether it will converge to some point. We have seen such intuitive curves, but like I said, I am just repeating, we do not have any mathematical criteria yet which tells us that well, given the system model, if we can just look at the system model, analyze it, and we can just directly say that well, this will have a stable output or when it will have a oscillatory output, or when the output will be not oscillating but rather eventually settling towards some final value. We do not have any such mathematical characterization of such responses. For this, we bring in this infrastructure of stability analysis. So, we will try to define what do we mean by stability of such dynamical systems, and we will then talk about that, well, how to analyze, given a dynamical model of the system, how to analyze whether the system would be stable or not. So by stable we mean that the system gives you the system design gives you a guarantee that once the system starts, eventually its response will be steered towards some target position in the state space. So let's understand in a physical manner first. So when we talk about stability, the idea is very old. So we can just take up an example of an ordinary pendulum. So let's say we have a free flowing pendulum here, and you just strike it like this with some force, and it goes to a position here. So if you see that if you just strike it with your hand like this, it will go to a position here, and then eventually it would roll back to this position. Will it stop? Not exactly. It will wander about a bit to this side, and then again it will come back a bit to this side, and then again it will come back, but again it will overshoot somewhere here, and slowly it will just settle down with the oscillations dying down like this. So this thing entirely is happening due to two reasons. You gave a force here, U, and then the system started moving with that force, but its movement got controlled by this gravitational force, right? And due to that, it was giving this oscillatory behavior here like that. Okay. So when we say by intuition that the system is stable, what we mean is it has a default target position. Let's say this angle is theta, and the target position is theta equal to 0 degree, or let's say 0 rad. And unless you are continuously applying some disturbance or external force, this is its stable position. It will eventually return back to this position with starting with oscillations, and then the oscillations dying down following this kind of an exponential curve here. This is the damping, right? And these are the internal oscillations that we just tried to create here, right? So that's why we can intuitively say that, well, this is what we can call that it's by default it's a stable system. Now let's just invert this thing. Consider the classical inverted pendulum example. So you have a pendulum like this, and let's say it is hinged here. Of course, we can understand that this is not a stable position. Here you have a mass m, so you have a force acting on it here, right, minus mg, like that. So even if you are able to successfully keep it at this position, with minor perturbation, wind or some noise or whatever, it will just get unstable, and eventually it will fall to some side. So this by definition would be an unstable system. Now this is called the classical inverted pendulum model in control theory, and there are several variants. For example, you have this cart inverted pendulum. So let's say there are wheels on the cart. There is a mechanical system where it is possible to apply some force, and the control objective here is that you use this force in a suitable manner, so that you have a control objective that you will target to make theta equal to 0. Okay. So by default this is an unstable system, and that is why you may require to design an external controller K, which at every iteration will inject these control forces to move this cart, so that eventually the system stays upright like this. So the point we are trying to make here is this by default is an unstable system, but if we consider the standard pendulum position with the mass at the lowest level, it's a stable system. So we have an intuitive idea what we mean by stability. The point is, for any dynamical system we can have a control objective, which is that it should eventually steer to some set point in the state space. Now the system, if it is inherently stable, that means its nature is that In case there are perturbations, the system will veer around a bit around that set point, but eventually by its own it will go to that set point. But if it's an inherently unstable system, the idea would be that if it is being perturbed slightly, it will slowly start building oscillations and it will go far away from that set point, that set point there, right? So that would be an inherently unstable system like this, and for such systems you will learn to build controllers, so that then with the plant and the controller together, your objective would be to make the system stable. So this still is not a very formal and mathematical representation of what indeed stability is. So let's continue and see. For example, here you have some illustrative examples taken from some well-known control theoretical literature. So we are showing that, well, there was a bridge built in Washington, and it was found to oscillate whenever wind used to blow, and eventually the bridge collapsed because the design of the system was not inherently stable. The designers failed to make the system stable with respect to perturbations from wind noise and other weather conditions. So based on this, we can have this kind of a pictorial description. We can say that, well, a system is stable when its natural response goes to 0 as the time approaches infinity. So if you remember from our previous discussions, we said that the system's time response will have two components. There is the natural response and there is also the steady state thing, right? So when this natural response, the initial oscillations do not build up and it dies down and only the steady state behavior remains, we would like to say that the system is stable. But if it is such that the natural response saturates towards infinity, it is never trying to come back to the steady state to some set point, we like to say that this is an unstable system. And we will say that it's a marginally stable system when its natural response is constant. That means, well, it is never settling down around the reference, but it is neither is it moving towards infinity as with time increasing, but rather it has a bounded oscillation. So suppose you have given a unit step and the system has got this. So here we are plotting only the natural response part, and we are saying that the natural response is dying down. Okay, so that's a stable behavior. Even this is a stable behavior because this is the over damped case. Eventually you are rising up and you are able to follow the trajectory. That is also stable. But if you have something like this, that where the natural response is keeping on increasing, it's unstable. And this is marginally stable because this curve trajectory tells you that, well, you are never going to settle down, it will just continue like this, but that oscillation is always bounded, so it's marginally stable. And even here you can have the output going beyond the reference, and slowly with time this difference is increasing even without oscillation, so that's also an unstable case. So that's how pictorially we can kind of sum this thing up, that what really do we mean by stability of a system. So if we now try to formalize a bit, we can say that, well, a system is stable in terms of bounded inputs, bounded outputs, or bistable if for bounded input disturbance that we provide to the system, the oscillation that we observe in the output is also bounded. So that would be a bounded input, bounded output stable system. Absolute stability means this behavior. That means eventually, the output response will be bounded and the output response will be damped, and eventually the output will just settle around whatever is the target position. And then we also have this concept of relative stability, that's the degree of stability. So that would be measured by observing the relative real part of each root. So for example, suppose we have two systems, and you see both of the systems will let's say for two systems, in this diagram we are claiming that R2 is relatively more stable than the pair of roots which are labeled as R1. So suppose you have a system which has got the roots of the denominator polynomial at these positions, and let's say you have another system where you have the pole located here. So the idea here is that, well, this is more into the left of plane, the negative real part is more, so the system would have more damping and the system should settle down faster towards its eventual reference value, and it's kind of more stable because it may be having lesser oscillations and the damping is larger here. So, the way we characterize stability is something like this, that well, suppose you are given this transfer function and you have figured out what are the position of the poles. If you see that all the poles have the real parts to be negative, we will say that the system is stable. And if you have some real parts of poles to be positive, we will say that the system is unstable. And this can really be observed here from our previous analysis and examples also, because whenever you are having all these poles with negative real parts, that means you are having a damping on the output, so that even with oscillations or without oscillations, based on the position of the other poles or the same pole with respect to the imaginary part, you may or may not have oscillations, but the damping is ensuring that eventually you are moving towards the reference. But in case you are having some pole with a positive real part, that would mean you are having poles in this side of this S-plane, and that would really mean that well, you don't have damping and your outputs will always be building up, and the deviation from the reference point is going on to increase like this. Okay, so there is no chance that your system in the steady state will settle down towards some reference. It may happen without oscillations like here, or it may happen with oscillations like here, depending on whether the pole has an imaginary part or not. But as long as the pole has a positive real part, you are not having damping, so this is the situation, it's unstable. If you have poles with no real part but only the imaginary part here, then you will have this kind of a marginally stable scenario like this, because you are just going to have oscillations, and due to zero damping, the oscillations are never going to die down. So we can say in a nutshell that stable systems have closed loop transfer functions whose poles reside only in the left half plane. Unstable systems will have closed loop transfer functions where at least one pole will be in the right half plane, or there may be more poles, that means at the same position. So poles of multiplicity greater than 1 are on the imaginary axis. So either you have at least one pole in the right half plane, and or you have poles of multiplicity greater than 1 which are on the imaginary axis. And you have marginally stable systems if with only imaginary axis poles of multiplicity 1, and you have other poles on the left half plane. So you have marginal stability if the transfer function has got poles in the left half plane and other poles which are only having their values where the real part is 0 and they are lying exactly on the imaginary axis. So that's how we can classify stable, unstable and marginally stable systems. And the next thing we will talk about is stability of closed loop transfer functions. So we will end this lecture right here and continue in the next class from this point. Thank you.